More nonlinear functions and their graphs. We just finished quadratics, and quadratics are nonlinear functions, but we have more. So let's get going on this. It says the domain of a polynomial function is all real numbers, and its graph is continuous and smooth without breaks or sharp edges. A polynomial function f of degree n and the variable x can be represented. Now this is a generic way of writing it down, and it takes care of any polynomial that you can think of. If I have a quadratic, I wouldn't have any of these terms here. I'd be starting with my x squared. Linears, okay, they are considered polynomials. If I, do away from the x squared on this way, I have linear. This one down here is a fifth power, so I'd have my largest exponent would be a 5. So this just represents, so it's nothing to get hyper about. Now each coefficient, a sub k, so a sub n minus 1, all of these a values are real numbers. My a sub n cannot equal 0. Talking about a quadratic right here. If I have a quadratic, a sub 2 can't be 0. If it were, then it would go back to being a linear. So if I have a quadratic, I have to have an a value other than 0. N is a non-negative integer. So my n values are non-negative. They're positive all the way down. So here is x to the first. This one would be x to the 0. The leading coefficient is a sub n, and the degree is n. Now leading coefficient is referring to the largest exponent you see, the number multiplying that variable, that's your leading coefficient. The degree, that's the largest exponent that you see. So in this particular problem, my degree is 2, the leading coefficient's 2. In this problem, the largest exponent I see is 5, so the leading coefficient would be negative 1. So a polynomial function of degree 2 or higher is a non-linear function. When you graph it, it's not going to be a straight line. So first thing we're going to look at with respect to nonlinear functions is identifying the extrema. Let me move this down. It says consider the following graphs of two different polynomials. Here's our old quadratic. I'm calling it old because we've had it. It's a parabola concaved up. This is a fifth power. Okay? It says the first function has an absolute min, whereas the second function has both a local min and a local max. For a function to have either an absolute max or an absolute min, it must be the largest y value for an absolute max or the smallest y value for an absolute min for all x in the domain of the function. So if I look at the whole entire picture, this one right here would be an absolute min because this point right here is the smallest y value that's going to occur on the whole graph. That's why it's called absolute, one and only. Now this one, on the other hand, this y value here, if I look at the whole entire graph, is not the smallest y value. But in this area, in this neighborhood, in this locality, or locale, well, in this section here, that is the smallest y value just in this neighborhood. This piece right here, just in this neighborhood right here, or in this locality, sounds good, that's the largest y value that I've got. But it's called a local max because it is not the largest y value that will ever occur on this graph. Now it says local extrema are defined on open intervals. So from one section to another on that particular interval, that's the largest, y value that I've got. On this interval right here, that's the smallest y value I've got. The function is continuous, but we have peaks and we've got valleys. Now we're going to graph the following, and we're going to determine any local and or absolute extrema. So best thing to do is graph and see what kind of picture you end up with. So I've got my calculator. So we'll go do this one. I've got a negative x to the fourth plus 4x, math for my cube, minus 4x. Let me ask it to graph. Now, I'm going to first put it back on zoom 6, because normally that's where we have it. I must have been playing with a curve earlier. But if you'll notice, it cuts off part of my graph, and this is my y value, so I want to make this y value here bigger, so that's my y max. So I think I'll go back in. Let's put 20 here, and let's see this graph. See if we can see it all. Okay, so if you'll notice, I've got a couple of peaks, I've got a valley, but this is the biggest peak. This curve is not coming back. Both ends are going to go to negative infinity. This is an absolute max. This would be a local min, and that will be a local max. And you know, you've seen me do enough of these videos. I always start left and I work my way over. So let's go find this one. And we've done max min before. We just haven't had to do all of these. We only had to do something with a quadratic. So second calc. The first one I had was a max, so let me go get number 4. So the left bound, I'm going to put in -2, and I'm going to put in 0. So see if I can get that inside my boundaries, and I don't guess. Okay, so now I wish they had this word maximum over here. Now it's not going to tell you if it's a local or an absolute. You've got to know that. But I would write this down. Let's see, let's go to the hundreds. At x equals -0.53, we have a local max of 1.45. You could say a local max of y equals 1.45 if you want to. But you could say it that way. Let's go get this one right here. That's a minimum. So second calc, number 3. So I got to get my boundaries again. I'm going to type in 0. And let's go 2. See if I've got it cornered. Okay. I don't guess. Should be blinking, so it is. So since this is a local, here's how I would say it. At x equals 0.65, there is a local minimum of -1.68. How's that? Let's go get this absolute fella. He's a max. So that's a number 4. So I'm going to put in 2, pick up where I left off. Let's go to, say, 6. As long as I have it cornered, so it's cornered in there. No guess. Alright, here it goes. At x equals 2.88, if I'm rounding to the hundreds, there is a absolute max of 15.23. And that's all I have to do. So hopefully you wrote those down. Let's see what I've got down here. And hopefully that's what we had just a few minutes ago. Yeah, I've got the last one up. So yeah, that's what we had just a few minutes ago. So you got to know the difference between a local and an absolute. Very, very essential. We've got another one. So let's go try this one. Let me go to y equals, clear this thing off. So I've got 5x to the third minus 12x squared plus 5x. I'm going to put it back on zoom 6. Okay, I've only got 2 things I have to worry about. I've got this value here and this value here. This is a local max, that one, and that's a local min. So let's go get our max. Second trace for the calc menu, number 4. So I'm going to put in -1 and 1. I don't guess. So here it goes. At x equals 0.25, there is a local maximum of 0.58. I do wish they'd have that word over here, but it's not, so I have to live with it. So let's go find this minimum. Second trace, number 3. So I'm going to put in 2? 2 might be too much. I think I'll change that. Let's make it a 1. I think that's where I stopped the other one. And 3. Okay, let's see if it'll be blinking on this down here. Yay. Okay, so here it goes. At x equals 1.35, we have a local minimum of negative 2.82. So let's see if that's what I've got right here. Yep. 1.35 local min, negative 2.82. Okay, so you need to go play with your max mins, and now it looks like, I guess we could make a couple of ideas here. When you have a larger exponent, you're going to have possibly more peaks and valleys. So unlike a parabola, okay, we only had one. So go play with these problems. Bye-bye.